Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, collect coins in a tree. This problem has many different solutions possible and you can solve this problem with some kind of greedy approach as well. But in this particular video, I would like to explain one particular concept which you can apply in many different problems of this kind, and that concept is really very helpful. We have also solved some problems in the past using that concept. I would link that video as well in the description down below or in the top right I section. I would encourage you to solve those questions by yourself after watching this video completely, and I'm very sure you will be able to do that, and you will see how powerful that concept is. So with that, let's get started. The problem states that you are given an undirected and unrooted tree with n nodes. You are given all the edges of the tree, and you are also given a coins array, which denotes whether the ith node contains a coin or doesn't contain a coin, right? So coins I would be either 0 or 1, denoting whether the node I contains a coin or doesn't contains a coin, right? Now you can choose any vertex to start with, and you will do the following operation any number of times. The operation is you will collect all the coins that are a distance of at most 2 from the current vertex, and you will move to any adjacent vertex in the tree, right? You need to finally return the minimum number of edges that you need to go through to collect all the coins and then coming back to the initial vertex again. So for example, if you start with node 1, you have to traverse to some edge to collect all the coins, and finally you have to again come back at node 1. So you have to return the number of edges that you have visited during your forward and reverse journey as well. So let's take an example. Let's say this is a tree. Node 0 and node 5 contains a coin. Other nodes then contain a coin, right? And here what they are saying is if we start with node 2, then you can see if we start with node 2, we will be able to collect all the coins of node 1, node 0, node 3 and node 4, right? But we will not be able to collect the coins of node 5. So at node 2, we collected the coin of node 0, and then we traverse this edge and go to 3. At 3, we can collect 5 because 5 is at a distance of 2, right? So we can collect the coin of 5, and finally we have collected all the coins. So only 0 and 5 had coin. So when we are at 2, we collected the coin at 0. When we are at 3, we collected the coin at 5. So we collected all the coins. Now we have to come back to the initial node. So initial node was 2. So we'll again traverse back this edge and come back to 2. So we have traversed two edges. One from going from 2 to 3, another while coming back from 3 to 2. Hence the answer here is 2, right? So hope the problem statement is clear. Now, as with every other problem, the first thing that you should do is, like, there are two different problems here. First, you don't know which vertex to start with. So you have to find that optimal vertex first. Secondly, let's say you know the vertex. Then also you have to find the minimum number of edges that you will need to go through to collect all the coins, right? So there are two different problems. So let's try to tackle first how to calculate the minimum number of edges that you need to go through for collecting all the coins, right? So the reduced problem statement is you are given a tree and you know which one is the root. So the root is fixed. You need to return what is the minimum number of edges that you need to visit to collect all the coins, right? So if you haven't thought about this version of the problem yet, encourage you to pause the video and try to think it yourself first before moving ahead. Now, how to solve this version? So as with every other tree problem, the simplest thing that you can do in this graph or tree is, let's say you somehow know the answer for the left and the right half of the tree, like all the child, you know the answer as already. So let's say The answer for this is x, and answer for this is y. So what does it mean? It means that you know that you have to visit x edges to collect all the coins in this subtree. Similarly, you need to visit y edges to collect all the coins in this subtree, right? Now, we want to find the answer for the entire subtree. So how exactly can you utilize x and y to calculate the answer for the entire subtree? The way you can do it is, so notice that from here you can collect all the coins that are at a distance of 2. So you can collect these coins, like any coin that is at this level, you can collect any coin that is at this level, and you don't need to traverse at all, any edge at all, if you have to collect any coins at these two levels. Now, when will you need to traverse an edge? You will need to traverse an edge only if you know that in the subtree there are at least one node which is which contains a coin and is at a distance of greater than 2, right? Because if there are, let's take this example itself. So here we see that from if we are at this particular node, we can cover or we can collect coins at these all nodes already. But we know that there are more than one nodes which contains a coin and which are at a distance of greater than 2. So if that's the case, then we are sure that we need to traverse this edge. There is no other option, right? Because to collect these coins, you need to be s- closer to this nodes, right? And there is only one path from root to any of these nodes because the given structure is a tree, right? So there's only one path. So you have to traverse this edge, that you have no other choice, right? So what we just saw is the trigger to understand whether we need to traverse an edge or not is to figure out if there, like, how many nodes are there which has greater than which are at a distance of greater than 2 and has a coin, right? If we know this value, then we can decide whether to move at that edge or not. So let's say somehow you know that value as well. So let's say in this case, along with x, you know that there are two nodes which are at a distance of greater than 2 and has a coin, right? So these are the two nodes we are talking about. Similarly, for this one as well, you know that there are three nodes which are at a distance of greater than 2 and has a coin. So we are talking about these three nodes. So these three nodes have a distance of greater than 2 and has a coins, right? Now, you will see, okay, this has non-zero value. So there is no other choice. I have to traverse this edge. Now, once you traverse this edge, you already know the answer for this node from before. So you know that you don't need to go downwards again. The answer for this entire subtree is x. So what you will doing, you traverse one edge, you know the answer for this subtree, and then you have to again travel, like, go back to the root because you have to traverse back to the original node as well, right? So every edge that you are traversing will contribute two times in your result. Now similarly, in the in this part of the child as well, you will see that the value is greater than 0. It means there are more than one nodes which have a coin and are at a distance of greater than 2. So you have to traverse this edge. There is no other choice. Now as soon as you traverse this edge, you will add plus 2 to your answer because you have to go there and come back as well. And once you reach here, you already know the answer for this edge, so that you will add. So along with this, you will add 2 plus y as well to your result. So this will be your final result for the entire tree, right? So hope you understand this part. Now, what's left? So this calculation of x and y is simple if you know the value for this, like you know this particular value, right? Because this is the exact trigger which will help us understand whether we need to traverse that node or not, right? So how to find this? So now the reduced problem is, given given a tree, find out, for each node, find out how many nodes are there which are at greater than 2 distance and has a coin, right? So that's what the reduced problem statement is, right? So this problem you can easily solve by using a BFS or DFS through each node. Let's say you want to find the value for this node. You will start a DFS or BFS from this node and calculate, like traverse the entire tree and see how many nodes are there which are at a distance of greater than 2, and that will be your result for this particular node. You can do this for all the nodes and get the answer. So what will it take? Each DFS or BFS would run in order n time, and you have to do this for all the nodes. So total order n square complexity, right? But this is not sufficient, because notice that we are still solving this reduced version of the problem. We haven't really thought about where to start. So even the reduced version of the problem can't be solved in order n square, because n is very huge. So that's where we need to optimize this for sure. Now, how to optimize this? Again, we will apply the exact same trick. Let's say we somehow know that, okay, for this node or for this subtree, what is the result? By result, I mean how many number of nodes are there which are at a distance of 0 and has a coin? How many number of nodes are there which are at a distance of 1 and has a coin? How many number of nodes are there which are at a distance of 2 and has a coin? And so on and so forth, right? So let's say you have this array here, and similarly you have this array for this child as well, right? So you know the number of nodes at a distance greater than equal, like at a distance of 1 is, and which also contains a coin, is y1, let's say, and number of nodes which are at a distance of 2 and also contains a coin, let's say y2. Now, given this, can you calculate the number of nodes that are at a distance of x from the root? The answer is yes, because let's say you are traversing one edge to go to this node. So if a node is at a distance of 3 from here, that particular node would be at a distance of 4 from here, right? So that's where we know that there are y1 number of nodes which are at a distance of 1. So there will be exactly y1 number of nodes in this subtree which will be at a distance of 2 from this node, right? And similarly we know that there is x1 number of nodes which are at a distance of 1 in this subtree. So all these x1 nodes would be at a distance of 2 from the root, right? So basically what we will do, we will simply add one one less index for all the children, and that would give us the value for the root, right? So in this case, for finding out what how many nodes are there which are at distance 1 and has a coin, you will just simply do y1, sorry, y0 plus x0, right? And for a 2 you will do y1 plus x1 and so on and so forth, right? Now you don't need to calculate everything in the right, because our goal is to just find out how many nodes are there which are at a distance of greater than 2. So what we can simply do, we can simply figure out how many nodes are there which are at a distance of 0, how many nodes are there which are at a distance of 1 and has a child and has a coin, and how many nodes are there which are at a distance of 2 and has a coin, and finally how many nodes are there which are at distance greater than 2 and has a coin. So these are the four things that we need to care about. You can skip this as well depending on how you implement, but for now let's say these are the four things we need to know about each of these nodes, right? Now this thing, because we are able to compose this from the results of the children, we can simply use DFS to figure out these values, right? Now, how to do that? Let's look at it. So let's say we have this exact same tree, and we want to calculate these four values for each of these nodes, right? Now, as always, we will start with the leaf nodes. So what are the values of the leaf nodes? At leaf node, there is no node which are at a distance of 1. There is no node which are at a distance of 2 or anything greater than that. So all of these values would be 0 for all the leaf nodes, right? So that's what we have done. We have put 0 in 1, 2 and greater than 2 columns for each of the leaf nodes, right? Now, for nodes, for counting the nodes which are at distance of 0, it means distance of 0 means the exact same node. We are talking about the exact same node. And what we want the count of nodes which contains a coin and are at a distance of 0. So we simply, that simply boils down to whether the node contains a coin or not. So in this case, the node contains a coin, so that's where the 0th index value was 1. This also contains a coin, so the value here is 1, but this doesn't contains a coin, so value here is 0, right? So that's the same way we have filled out all the children's. Now, as we discussed, the value for parent would simply be the addition of one index less of all the children, right? Because number of nodes which are at a distance of 1 and has a coin would be equals to number of nodes which are at a distance of 0 from here, because one distance is already covered here. So number of nodes which are at a distance of 0 and has a coin, number of nodes which are at a distance of 0 and has a coin. So that's what this index is giving us, right? So we will simply add these two, and that would give us number of nodes that have a coin and are at a distance of 1. Similarly, for this one, we will simply add the index 1. So 0 plus 0, which is 0. Now, finally, for greater than 2, we will add these two columns completely, right? Because this means this says that there are 0 nodes which are at a distance of greater than of which are at a distance of 2, but this all nodes will be at a distance of 3 from root node, right? So basically this will translate to greater than 2 column. So we will just add these two and add these two and put the value here, right? And what will be the value for 0th index? It will be 1 or 0 based on whether it contains the coin or not, right? Now, in the same way, let's find the value for this. We already know the values for all of these nodes, so simply we can, once we find the value for here, we can simply ignore this entire tree and assume that there is single node which have this value, right? So that's the standard way how we do recursion during DFS in the tree, right? So once we have all these values, we can find this the value for this node as well. So for 0th index, it would be 0 because this node doesn't contains a node. This node doesn't contains a coin. For index 1, again, we will sum all the things at index 0. So 0 plus 1 plus 0. So the value here would be 1. For this one, we will sum everything at index 1. So 1, 0 plus 2 plus 0. So value here would be 2. Right? So it means there are two nodes which are at a distance of 2 and has coins. So these are talking about these two nodes. Right? Now, similarly for this one, we will sum this entire piece, and this entire piece, right? So everything is 0, so the value for this would be 0. Now, in the same way, we calculate the value here. The 0th index would be 1 because it contains a coin. The first index would be simply the value for 0th index. There is no other child at all, right? So this would be value of 1. Basically, whatever comes here should be here, right? And the value for here would be the sum of these two. So it would be 2, right? The same way, let's calculate the others as well quickly. So here the value would be 0. Here it would be 1 plus 0 plus 1, which is 2. Here it would be 0, and this as well will be 0. Now finally for this one, this will be 0 because it doesn't contain coin. The first one, it would be 1 because 0 plus 1. Second one, it would be 2 and then 0. Now, finally, this entire tree, that the root node, we'll just look at 0 would be 1 because it contains a coin. First one would be 0 plus 1, 1. Second one would be 1 plus 1, sorry, 1 plus 0, it is 1. And the last one would be 2 plus 0 plus 1 plus 2, so 5, right? So this is the exact values for each of these nodes. Now, remember, this is just a utility for finding out the exact result. The exact result that we want was number of edges that we need to visit. But what we, like, just to recap that particular pass, we what we have said is, if we somehow know the number of nodes which are at a distance of greater than 2, we can decide whether to go left or right. And if we will simply like consider the value, the actual result of these two nodes. So if the result of this node is x, that is, we need to visit x edges in this particular, if in this particular subtree, to collect all the coins. Similarly, we have to visit y edges to collect all the coins. Now, if we know number of nodes greater than which are greater than 2 value, or which are at a distance of greater than 2 and has a coin, we can decide whether to visit this particular child or not. So if we want to visit, we will add plus 2 to our result. If we want to visit this child as well, we will add plus 2 to our result. And as and when we are visiting something, we will consider that particular values as well, right? So let's say we decided to visit this particular child, so the answer would be x plus 2 plus x plus 2, that's the answer. But if we decided to visit both the child, the answer would be x plus 2 plus 2 plus y, right? So that's what we will be doing. So for each of the leaf node, the answer again would be 0, right? Because we know that from leaf node, we don't need to visit anything, because there is only one node, and if that node has a coin, we can simply collect it. There is no need to visit any edge at all, right? So for all the leaf node, the result would be 0. That is, we need to visit 0 edges to collect all the coins. Now, for this for this node, how to calculate the result? Again, we need to understand whether we have to visit this edge or not. Now, what is the trigger? The trigger would be, figure out how many nodes are there which has greater than equals to 2 value, which have like which are at distance of greater than equals to 2 and has a coin. So why we are looking at greater than equals to 2? Because the node which will be at index 2 would be at a distance of 3 from the root, right? So here we will say, okay, there are 0 nodes which have a coin and are at a distance of greater than equals to 2. So basically, we don't need to visit this edge at all, right? Now, what about this one? Again, same logic, we'll see we don't need to visit any of this edge. So the answer for this would be 0 again, right? Now, what about this? Here again, the same logic. We'll see whether we need to go down or not. So the trigger for going down would be, check how many nodes are there which have greater than 1, which are at a distance of greater than 2 and has greater than 1 coins. So in this case, there are 0 coins. Like, there are 0 nodes which are at a distance of greater than equals to 2 and has a coin. So basically, we will not visit this edge at all. The same way, we will not be visiting this edge as well. So answer for this one as well would be 0, right? So what does it mean? It means that if we have to calculate, if we have to collect all the coins in this particular subtree, we don't need to visit any edge at all. And you can see this is logically correct as well, because the height of the tree is 2. So you can actually collect all these coins without visiting any edge. So that's why this 0 is correct. Now, what about this? The answer for this would be again 0. You can follow the same pattern. Answer for this would be as well 0. You can follow the exact same pattern. Now, let's try to calculate the answer for this. So here we need to understand whether we will visit this edge or not, right? Now, what is the trigger? Trigger would be, understand how many nodes are there which have greater than 1, like which have a coin and are at a distance of greater than equals to 2. So there are two nodes, right? So there are the number of node is greater than 1. So we will be visiting this edge. Now as we are visiting this edge, we will add plus 2 because we need to go to this node and then come back as well. So we'll add plus 2 here in our result. And once we are at here, we already know the answer for this node. Like once we are here, we know without visiting any node, we can collect all the coins. So basically the answer for this node would be 2, right? So we are visiting two edges to collect all the nodes in this particular subtree, right? Now finally for this one, again let's see if we need to visit this edge or not. Let's look at the sum of these two values. The sum is greater than 0, so we have to visit this, right? So plus 2 in our result. Now once we visit this, we know that at with 0 edges we can visit all, we can collect all the coins after visiting this, after we reach this node. So 2 plus 0. Now let's try this edge as well. Do we need to visit this edge? Answer again depends on the sum of these two. The sum is greater than 0, so we will be visiting this edge. And as we are visiting this edge, this will add plus 2 to our result. And the value of this edge as well will be considered because we are visiting this edge, and this says that from this edge we need to visit two edge to collect all the coins in this particular subtree. So finally the value for this node is 6. Why 6? Two edges, like two edges for here, and then 0 edges after this node, two edges to go there, and then two edges to collect all the coins in this particular subtree. So that's where the answer here is 6. So that's the way you can calculate the number of edges that you will be visiting to collect all the all the coins, right? So let's quickly look at the pseudo code. So there are two things here, two major things that we were doing. Firstly, we calculated these things, right? The number of nodes which are at a distance of 0, which are at a distance of 1 and has a coin, which are at a distance of 2 and has a coin, and so on and so forth. So for that, we we figured out that we need to merge two things to get the value for the root. So that's what the first merge function is doing. So first merge function is doing that, let's say we want to calculate the result, or we want to merge the value for source into this target. So what we'll be doing, we will add source of 0 to target of 1, right? Because number of, so what it means that number of nodes which are at a distance of 0 will be exactly similar to number of nodes which are at a distance of 1 from the root, right? Similarly, target of 2 plus equals source of 1, and finally target of 3 plus equals source of 2 plus source of 3, because target 3 means any nodes which are at a distance of greater than 2 and has a coins. So the node which are at a distance of 2 as well will be at a distance of 3 from the root node because of one extra edge, right? So that's what we have done. So this is the first merge function. With this merge function, we will be able to calculate these all arrays value, right? With the simple DFS. Now, second merge function was we need to compute the number of edges that we are visiting, that we need to visit to collect all the coins in the subtree. So for that, what we have done, we simply looked at whether we need to visit this edge or not, and the trigger for this was calculate how many nodes are there which are at a distance of greater than 2 and has a coin. So that's what we are doing. We need to, let's say, figure out the target time, right? And we already know the coins of the source, basically this array, right? And we also know the source time, basically this number, right? So these two things we know. Now from these two things, what we will be doing, we will be just figuring out what is the sum at index 2 and greater than 2 values, If sum is greater than 0, it means we have to visit this edge. So for visiting this edge, we will be going to this edge and then coming back as well, because we need to go back to the original node as well. So we are adding 2 for that, like because 2 edges will be required. And we are also adding the value of the source node, because we are visiting this edge, but after that we may also need to visit some other edge, and this number actually denotes the same thing. This number denotes that how many edges you need to visit in to collect all the coins in this particular subtree. So that's why we are adding source time as well. So these are the two merge function that we need to look at, that we need to take care of. Now once we have these two merge function, we can simply write a DFS that can give us like that can help us calculate both the values for all the nodes. So we'll start with any, so like the exact root and a dummy parent for root, let's say -1, and we will check if the current node has a coin. If current node has a coin, we will populate the value of 0th index to 1, otherwise 0th index would be 0. And then we will look at all the child and merge the coins of the child and merge the mean time of the child as well. So before this, so after, okay, so there is one small correction. So after this, um, we would also be doing DFS of child comma SRC, right? So this is how we will be able to calculate all the values for each of the node. So finally, the min time. So min time is nothing but number of edges. So I represented it with time somehow during the contest. So that's why I am writing time here. But it is the number of edges. So finally, the min time of this node, of the root node, will give us the result that we want. That is the number of edges that we need to visit to collect all the coins in the entire tree, right? So hope this entire thing makes sense. Again, strongly encourage you to watch the previous part, like the video till now, and understand this concept before jumping to the next part, because next part is all about the original problem. So currently we have just solved one part of the problem. There is, that is, find the minimum number of edges that we need to go through if the initial vertex or the root node is fixed, right? But let's say in this problem we are given that the root node is not fixed. We are free to choose any root node that we want. So what we would be doing, we will try this DFS for every root node. Like we let's say we will consider that, okay, this is the root node first, then we'll say, okay, this is the root node first, and then do again BFS, again do the same DFS, and see which one is giving you the smallest value of the root, like a smallest value, and the one that will give you the smallest value would be your answer, right? So what is the time complexity? The time complexity in that case would be, you will be applying DFS for each root. Like you will consider every node as root one time. So for each root you are applying a DFS which will take order and time. So this would be the time complexity. And again, this would not pass because n here is huge. So we need to reduce this as well. Now that's the exact same thing we'll be looking at. We will be looking at how to calculate the value for each of these nodes when these nodes are root in less than order n time. Basically, we will not do DFS for each of these nodes, but still we will be getting what is the value when that particular node is the root node, right? So let's just to reiterate, till now we have these two arrays built out. So we have min time subtree and coin count subtree. Basically, min time subtree denote what is the minimum time, or what is the minimum number of edges that we need to visit to collect all the coins in the subtree of a particular node I, let's say. Similarly, coin count subtree nodes, this array that we have calculated. So this didn't like coin count array would be a array for a single index. So coins count array for index I would look would have four values. First one would denote the number of nodes which are at distance 0 and has a coin. Second one, number of nodes which are at a distance of 1 and has a coin. And third one, distance of 2 and has a coin. And fourth one, which are at a distance of greater than 2 and has a coin. Right? Now, let's see the next part. Next part is we know the values for each of these nodes when one particular node is the root. That's what we have calculated through the DFS, right? We want this exact same value, let's say, when this node is the root. Now this node is not the root. Instead, let's say this node is the root, and we want to calculate the exact same thing. So how would the tree would look like? So basically, when this node would be root, this all part, this entire part would become a child of this node, right? So this is how the structure would look like. So this node, these all structure would remain as it is. So this structure is remain as it is. And for this entire structure, this will become the child of the new node. So that's what we have done, right? So this is how the new tree would look like, right? Now, I would encourage you to pause the video and think of which which all values would change due to this restructuring, right? Hope you have thought about it. So only values which would change are this and this, nothing else, right? Why? Because if you think about it, this node, the value for this node, that is 1115 or this 6 was was taking into consideration that this node has two child. So this node is equals to this node, right? So the value here was calculated based on the fact that it has two child. But now it has one of these child only, other child is now gone, right? So that's where this value would change. Similarly, for this node, the value was calculated based on the fact that it has two child. But now this node has three child, right? So one, two, three. So these are the only two nodes whose value will change. Nothing else would change in this entire structure, right? And we can easily compute the values for these two nodes. So basically this would change, this would change, this 6 would change, and this 0 would change. And we have to calculate the new values for each of these. Now, what will be the new values for this? What will be the new value for this? Again, the value, previous value 1115 was, okay, let's just take this as well. So hope this is visible. So what we are doing is we previously the value 1115 was computed by merging this and this, right? But now there is only one child. So we will only be merging this and not this, right? So one way to compute the new value for this node is simply remove the contribution. So remove the contribution of this node from this value, right? And that would give us the new value for this node. So let's do that. So the value of this node was 1115, and we have to remove the contribution of this node which was 0120, right? Now what does removing contribution mean? This 0 has contributed to index 1, right? Similarly, this one has contributed to index 2. This 2 has contributed to this greater than 2. And finally, this greater than 2 also contributed to greater than 2. So let's remove each of these. So 0 will stay as it is because 0 doesn't, uh, the value at 0 was not calculated based on any contribution, right? So this will stay as it is. For 1, we will subtract whatever the value of 0th index was. So 0th index was 0, so we will just 1 minus 0, which is 1. Now for 2, again we will subtract whatever was the contribution from the first index. So it will now become 0, right? Now finally for 2, we will subtract the contribution of these two nodes. So this 2 was like, these two contributed 2 to this 5. So we'll just remove it and the new value would become 1103 for this node. Now, not only this, the exact result of this node will also change. Basically, this number denoted that how many nodes or how many edges you need to visit in this particular subtree. So previously, this subtree contained both this subtree and this subtree, and this 6 denotes that we have to visit 6 edges to cover all the to collect all the coins in the entire tree. But now it only covers one particular subtree. One subtree has gone. So the same thing again, we will just remove the contribution of the previous subtree. So what was the contribution of this subtree? Contribution of this subtree was two things, right? First, like, we will check if we need to visit this edge or not. And to check that, we have computed what is the sum of the index 2 and index greater than 2. If the sum is greater than 0, then we have contributed plus 2 because this edge was visited, and it also, we have also added the exact value of this node, right? So this this node, this 6, has a contribution of plus 2 from here and 0 from here. So basically, in total, it has a contribution of 2 for this entire subtree, right? So to remove that contribution, we can simply subtract 2 from here. So the new value here would be 4. So what does it mean? It means that we need to visit 4 edges to collect all the coins in the entire subtree, right? Now, we have recomputed the values for this. What about the value for this? So the new value for this would be, so what has changed? Think about it. Previously, this entire thing, the contribution of this node was containing the left part and the right part. We merged these two, right? Now this two is intact, right? So there is no contribution change because of this two. But there is new addition now. There is one new children, right? And this will also contribute to this result. So what is the value for this children? The value for this children is 1103. So now this 1103 will actually contribute to the value for this node. Now, what was the contribution formula? So if just to recall that, this was the contribution formula, right? So you'll simply add 1 to second index, 0 to first index, and so on, right? So basically, the current value is 0, 1, 2, 0. In the 0th index, we will not make any contribution. For first index, we will add the value of 0 here. So it was 1 from before, and we got one more 1. So it will become 2, right? For this one, there was 2 from before, and we have to add one more. So this will become 3, right? Now this was 0 from before. This was 0 from before, and we have to add 0 plus 3. So basically, we have to add 3, and this will become 3. So this is the new value for this node. Now, what is the min time? If you remember, like, we also have to calculate the number of edges, right? So what is the number of minimum number of edges that we need to visit? Again, same thing. We'll we know the contribution of these two nodes already, and that sums to 0. Now we also have to add the contribution of this new node. Now what we will be adding? We will be first checking whether the value of index 2 plus index 3 is greater than 0 or not. So index 2 plus index 3 here is 3. So it is greater than 0. So basically we need to visit this edge at any cost. So this will be contributing plus 2 to our result, and this plus 4 would also be added, right? Why? Because plus 2 only denotes that we are reaching this edge. Now after this edge we just need to uh, follow this number, because this number denotes what is the edge we need to visit for this entire subtree. So we will be adding 2 plus 4 6 to this, and the new value would become 6, right? So this is the new value when this node is will be the root, right? So just to reiterate what we what we have done, firstly we want to calculate, we know the values for all the nodes when this node is the root, right? And now we want the value for all, like value for this node when this node is the root, right? To calculate that, we could have simply another DFS, but doing another DFS was not time friendly, because it was leading to order n square complexity. So what we have identified is, okay, let's try to restructure the tree. And after restructuring the tree, we identified that there are only two nodes which will be changing, and we can simply calculate the new values of those two nodes only. And calculating the value for those two nodes only was very simple. We One node was getting one contribution removed, and one node was getting one contribution added. So for the node which was getting a contribution removed, we just removed the contribution of the previous node, and for the nodes which was getting a new child added, we added the contribution of the new node. And finally we got the value for the node, assuming that this will be the new root, right? So hope this makes sense. Let's just take one more example to understand this a bit more. So let's say we know the what is the value when this is the root, right? Now let's try to calculate what is the value when this node is the root, right? So how would the tree look like? The tree would look like this node will be the root, so this will become a child, and this will become a child of this, right? So basically this structure would remain as it is. This is now becoming the root, right? So this node will become a child of this node. So the structure would look something like this, right? Now one thing to note here is that whatever we have done previously is something that we have to retain, because as we keep going downwards, whatever changes we have made to the tree structure would stay as is. So basically once this is the root, this node will become a children of this node, right? So this entire structure would be a children of this one, right? And no matter how much deep you will go, this statement will always be true, right? So that's where we have retained the values that we have calculated previously. So we have calculated the values for when this node become the root. So we calculated that value 1103. So we retained that value, and now we will be calculating the value for new changes. So again, as discussed previously, what will change? Only two things will change. One node. So this becomes the root, right? So this node is now getting this contribution removed, right? And this node is now getting this contribution added, right? So that's the two changes that we have to again apply. Now first thing, what was the, okay, I haven't wrote the value. So the value was 0233. So the previous contribution of this node was 0233. Now this contribution was there assuming the fact that this node has three children, 1, 2 and 3. But now this children is removed. So we have to remove its contribution completely. So what was the contribution? Again, contribution was 0200. 0 contributed to the first index, 2 contributed to the second index, and 2 and 3 contributed to the third index. So let's just update the contributions. For 0, there is no contribution, so it will remain 0. For first, it was contributing 0. So subtract 0, so it will become 2, right? For second, it was contributing 2. So 3 minus 2, it will become 1. For third, it was contributing 0. So it will remain 3, right? So this is the new contribution now. And what is the value? So the previous value was 6, right? The new value would be 6 minus the contribution of this node. Now, what was the contribution of this node? Contribution of this node was 0, right? Why? Because we decided not to go at this edge at all. Because if you remember, the definition was we will first check the sum of second and third and then count the contribution. So that's what we have done. This will not contribute anything because the sum is 0. The initial sum was 0, so this will not contribute anything, and hence this 6 would remain 6, right? And what does it mean? It means that we have to visit 6 edge to uh, collect all the coins in this particular subtree, right? Now, what will be the updated value of this node? 0220 has these three edges considered. So now let's just consider one more edge. And this edge, again, the same thing, contribution 0213. So we'll just add corresponding indexes. So for 1, it would be 0. For, sorry, not 0. 2 was there, right? So 2 plus 0. For 2, 0 plus 2. So it will become 2. For 3, 0 plus 1 plus 3, 4. So it will become 4, right? And now what is the actual number of edges that you need to visit? So initially it was 0 because of these 3. Now what is the new contribution? Again, we need to check whether we need to visit this edge or not. And to check that, we need to calculate the sum of these two indexes. Then the sum is greater than 0. So we have to visit this index. So this will contribute plus 2 and this node will contribute 6. So basically 0 plus 8, and 8 is the new updated value, right? So it means that if this node is the root, we have to visit 8 edges to collect all the coins, right? So hope you got the idea. What we are doing, we are simply doing another DFS and calculating the contributions of the two changed nodes every time, right? So just to give you a bit more intuition, what we are doing is we know what are the values if this node is the root, and what we want, we know we want that what is the value if this node will be root. So what the observation is, if we simply, so if this node is the root, only thing that would change is this edge, the direction of this edge. This edge is pointing from C, like from this node to this node, but after this node is the root, the direction of this edge would be reversed. And if the direction is reversed, only two nodes will be affected, this one and this one, right? So when we know the value for this node, we can simply reverse the direction of this edge and calculate the value for all its children when they will be the root, right? So by just reversing the direction of all like of the like immediate edges, we can calculate what is the value when this node is the root, or what will be the value when this node is the root, right? And once we have found that okay, what is the value when this node is the root, we will apply the same exact trick. We'll say okay, we know what is the value for what is the value when this node is the root. We can simply reverse the direction of immediate edge and calculate the value when this node is the root, right? So That's what we are doing. And why every this entire thing we can do, because only two nodes were changing. And why two nodes were changing? Because each node has exactly one parent. Had it been a graph, there will be something of there will be edges like this. So each node will have more than one parent, or one outgoing, one incoming edges as well. So we will not be able to apply the same algorithm at that time. So this algorithm is only applicable to tree, because it is guaranteed that each node will have exactly one outgoing edges, exactly one incoming edge. And we can simply, if we want to make that node as the root, we can simply reverse the direction of that edge, and this node will become the root, right? So what will be the pseudocode look like? So what we are doing, first of all, we are doing two operation. Firstly, we are removing the contribution of coins, and secondly, we are removing the contribution of edges. So those two function would be exactly reversed of the original function. So if you remember, merge coins had plus operator here. Now remove coins will just have minus operators, right? Similarly, merge min time, merge min time had, this would be remove min time, right? So merge min time had plus operator here, but remove min time would just have minus operator here, right? Now once we have these two, what we are doing, we are starting the DFS from the root. So let's just, so we are starting the DFS from the root, and we know the value for the new root already. So basically, initially we already know the value when this node is the root, because that's what we have computed previously with the previous DFS. So we already know the value. Now in the first iteration, we will calculate the value for each of its children. And how we will do that? We will just reverse this particular edge. So let's say we are considering this child first. So for this child, we will do two things as we have discussed. So we will do two things. First, we will remove the contribution from the parent, right? So parent was root and child was child, right? So what we have done, we computed two new things: count coins except child, right? And this, initially we initialized it with the value of the root. So initial, what was the initial value? 0, 2 to 3, right? And then we removed the coins of the current children. So what we have done, we removed, this was the new, new value. We removed the contribution of the child, right? And then same thing we will do for min time, or minimum number of edges. So we initially we know the minimum number of edges was min time for root. If you remember, we have calculated that previously. So we know the value, and then we will remove the min time of the current child, right? Now after we do that, we have two new arrays: count coins except child, min time except child. So we have these two things built with us. Now what we need to do, we need to add the contribution to this node. Or what we will be adding, we will be adding these new contributions. So that's what we have done. um, this is the count coins root, which basically denotes that if this child is the root, what is the count of coins. So we have initialized with the count of coins of subtree, basically what we have computed before. So what was the count before when we only consider subtree. So we initialize it with that, and then we will merge the coins of current new root, like basically the root except the child. So we just calculated that before, right? So we just remove that contribution. We'll merge that contribution, and similarly we'll merge the same contribution to min time as well. So previously, min time or min number of edges was min time for subtree, right? and we will just merge the current mean time except child in this, right? So after you do this entire operation, we got the new values for this root, right? So once you got the new values for this root, you can calculate the same values for each of its children as well. So just to uh, again iterate, once we have calculated the value for this one, we can simply calculate the value for this one, right? So that's what we have done. So that's the same thing we are doing. Once we calculate the values for a particular child, when that child is the root, we can simply calculate the value for all of its children. So we'll just simply call the same DFS, and that will do the exact same thing. Basically, it will reverse each of these edges uh, as and when it is going downwards, right? So this is the entire code. Now, I would encourage you to rewind the video. I would be putting exact timestamps of different part of the video, explain different concepts in the description. You can move back and forth in different part of the video. If you don't understand a particular part, I would strongly encourage you to rewatch that particular part of the video. I'm very sure that you will be getting it. And finally, as always, try to code this solution yourself first before jumping to any other uh, jumping to looking at any other code or even my solution itself, because if you code this solution yourself, you will be able to retain this concept for a much longer time. So with that, the next section will be looking at the exact code for this problem. The code is exactly what we have discussed. So we have this four function: merge coins, remove coins, merge min time, remove min time. Merge coins, as we have discussed, it will simply be uh, target at one uh, would be we will be adding source of 0 because of the reasons we have discussed, and similarly target 2 will add source of 1, and target 3 source of 2 plus source of 3. So this is merge coins. Remove coins, again exact same thing with reversed operators, right? Same thing for merge time and remove min time as well. So we'll check the whether we need to visit that edge or not. If we need to visit this edge, we'll add 2 plus source min time, right? Again, remove mid time is exactly similar. We check if we have visited that edge. If we have visited that edge, it means this much was contributed. So we'll just subtract that, right? Now after these two, we have this DFS in. This is the first DFS that we are uh, doing to calculate the values when a single node is the root, like when any node is the root. So this is the first DFS that we have done, right? So that's what we have done. So the code is very similar. We iterated over all the children, we calculated the values for all the children, and then we merge the values for all the children. So this count coin subtree of source is the current count of coins for this particular source node. We are merging count subtree of child. Similarly, for min time, we are merging sub min time of child with min time of source, right? Now, after we have done this, we know the first, like we have calculated already the first DFS, or for a single node, what is the value for all the other nodes. Now we have to reverse the edges one by one, right? So that's what second DFS is doing, DFS out. So before looking into this, let's look at the main function first. So what we have done, we have just simply reset the values because we have some global variables here. After that, we build the tree, basically adjacency matrix. After that, we do DFS in to calculate the values for a single node. And after that, we want to calculate the values for each of these nodes when they are the root. Right? Currently, we have calculated that if 0 is the root, what will be the value of each of these nodes? But now we need to know if 1 is the root, what is the value for each of these nodes? Or if 2 is the root, what is the value for each of these nodes, right? So what we have done, we know that when 0 is the root, what is the value? So we just uh, initializes it. So we initializes count coins of root with count coins of subtree, because we already know that 0 was the root. So whatever the value of its subtree was would be the value when this node will be root, right? Similarly, for min time, we know that because this was already the root, so whatever the value for its subtree is exactly considering the entire tree with 0 as the root. So we initialize these two things with the subtree part, and then we call DFS out. In DFS out, we are just reversing each edge one by one. So we visit all its children, right? Now let's say we visit this children first. So will just reverse this edge. Now what does reversing this edge means? It means that remove the contribution of this from this, and whatever the new contribution will be there, just add that contribution back to this one, right? So that's what we have done. We removed the contribution for coins. So coins except child, we initialized it with the coin coins when root was the root, right? We initialize it with this. Now after that, we removed the contribution of the subtree of child, right? So after we remove the contribution, count coins except child would contain all the coins except this particular child when this node is the root, right? After that, we also did the same thing for min time. We calculated the min time for the root and removed the contribution of the child. After that, we added the contribution of the new count coins except child and min time except child to the child node, because now child is the root. So these things would become the children of this child node. So that's what we have done. We initialized count coins of root. So remember, like there are two things: count coins of root and count coins of subtree. Subtree would contain what is the count of coins or what is the min time for the subtree, but count coins of root or min time for root would be what is the min time when this node is the root. So when child is the root, what is the count of coins? So we have initialized it with the subtree, because we know that whatever subtree was there previously, they will be contributing as it is. We just need to add one more contribution. So we initialize it with that, and we just added one more contribution here, right? Same thing for min time. We know what was there previously will be there as it is. We just added one more contribution for the min time, right? And we finally call the same thing for its like the children of child as well, right? Now this problem, this concept was is also known as in out dp or deep, like it is a very, if you search in out dp you will get to see this exact same concept. Now this problem was a bit difficult for in out dp. So if you have understand this problem, well, good. I would encourage you to try out other simpler problems of in-out DP first. I would link some of these in the description down below. I have also solved some of them in this channel itself. You can watch that video as well. You will be able to understand that concept uh, now. So hope you enjoy it. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.